This is where all this, actually, where field theory started. So this was the first quantum field theory that was constructed and understood. And where the Feynman rules were first formulated. So it describes interactions of electrons with electromagnetic fields, with photons. And then, okay, it's clear that, and we already know how to quantize free electromagnetic field and free electrons using Dirac equation, Maxwell equation. And so now we need to formulate what are the Feynman rules. So we need to understand the propagators and see what is the interaction versions. So the propagators are determined by free fields, right? So the propagator is, for instance, for photons, the propagator will be the time-ordered product of two fields. And so these are built from oscillators in exactly the same way as for, so they, in the gauge that we have chosen, the Coulomb gauge, they behave as four independent scalar fields. So the propagator will then be equal to four independent scalar propagators. And then photon has mass 0. So in momentum space, the propagator is just minus I g mu divided by p squared. Yes?
Sorry, you said this is equivalent to for independent oscillators. What precisely is equivalent to four independent oscillators?
It's, we can treat any a mu with any, I mean, mu and index mu just labels four fields. So we can treat them as if they were just four independent scalar fields. Now, the truth is that the propagator will depend on the gauge. So if we have chosen the gauge in a different way, the propagator will be different. And Feynman rules will be different. So the reason for that is that the field itself is not a gauge-invariant observable quantity, defined up to gauge transformations. And so the dependence on the gauge chosen will cancel in final answer for observable quantities. Since this will happen anyway, we can pick up any gauge we want. So in the Coulomb gauge, the answer is particularly simple, and we will use it throughout the course. So usually the photon propagator is drawn as a wavy line. And now endpoints, they are characterized by, in the presentation, by their positions, but also by the Lorentz indices. And in momentum space, we also need to specify the momentum. Yes?
So I have two questions. So first question, how does the metric G mu count this expression? I mean, is there any connection between this expression and the expression of the stable field property? And also, mentioned that if you have different gauge, then the propagator is different. So every time you fix the gauge.
So just to quantize the field, you need to fix the gauge. Otherwise, it's impossible. So
Is there any connection?
well, to write down the propagator, you need to quantize the field. You need to express it in terms of oscillators. And that would be different in different gauges. But for now on, you don't need to think about it because, well, you just pick this gauge for now on. And we can work in it and work out any expression in this particular gauge. The answer is anyway independent on the gauge choice. So concerning G mu, this is well, this is the first of all, this is the only Lorentz invariant expression that you can write, and it appears here because the commutators of the ladder operators in A, so they commute on G mu. Okay, so this was so we know how to write down the propagator of photons. Then we need to understand the propagator of the Dirac field. And the Dirac field describes fermions. So for fermions, well, again, we can introduce the field as a vacuum expectation value of T order product of two field operators. Actually, this.
Did you say that is the field?
Sorry?
Did you say that is the field?
Didn't get you.
This expression for the propagator. Sorry.
So this is, we take the, as usual, we take the T-order product of two fields and that defines us the propagator. So for, if you take two psi's, the result will be 0. Well, the formal reason for that is that psi contains annihilation operators for electrons and creation operators for positrons, which commute with one another. So these fields commute, and so they will produce 0. The physical reason is that psi has charge 1, and so to have a non-zero expectation value, you have to insert. So the operator here should have total charge 0. So we have to have psi bar inside in the matrix element. But then psi is a fermion, and for fermions, one has to take into account their anti-commuting nature. So the operators in this field stay anti-commute instead of commuting. So the time order product for fermions is also defined in a different way. Or psi alpha of x, psi bar beta of y is defined to be psi alpha psi bar beta if x0 is larger than y0, but if y0 is larger than x0, then we interchange their order but also change the sign. So under the sign of time ordering, the operators anti-commute rather than commute. So we take into account the statistics of the field. And then we also need to calculate this matrix element to find the propagator. Now the analogy with scalar fields is useless because Dirac field behaves quite differently. So we need to calculate it anew. And to do it, we can go through this calculation of the Schwinger term. So we apply the Dirac operator to the propagator. So we can act by Dirac operator on S of x minus y. So naively, this would be equal to 0, because the Dirac operator annihilates the field. But we'll pick a Schwinger term. So let me omit the calculation. So the result is that on the right-hand side, we will get the delta function. So then we Fourier transform this equation. So ID becomes the momentum. So the Fourier image of the Dirac field satisfies this equation. So this is a matrix equation. I don't write indices here, but it is understood that the Dirac operator is a matrix, 4x4 matrix. S, as you see, is also a 4x4 matrix. And so this is a matrix equation with the unit matrix on the right-hand side. And so is this equation. So to find this, we need to invert. We need to invert a 4x4 matrix. So S of P is equal to I times the inverse of the 4x4 matrix that has this form. Unfortunately, there is a trick to do it. Namely, we know that P plus M with the slash times P minus M gives the Klein-Gordon expression P squared minus M squared times the unit matrix. So we can then take the inverse of this equation. This is a product of two matrices. The inverse of product of two matrices is product of inverses taken in the opposite order. And on the right hand side we have right. So then we multiply this equation by P plus M from the right. And so on the left hand side we get what we wanted to compute. While on the right hand side we get P plus M divided by P squared minus M squared. Therefore, the Dirac propagator is, okay, let me write it in the coordinate space. So it's given by this expression. And usually is depicted by a line with an arrow. So the arrow here denotes the flow of charge, because now the field carries a charge. So you see, if we inserted field psi at point x and psi bar at point y, the convention is that we connect. So the arrow shows the direction from the psi to psi bar. And in principle, so there's also a momentum arrow which can coincide with this arrow or be opposite. But then we need to take into account that so P that stands here, so that the propagator is written here, corresponds to the arrow, these two arrows being in the same direction. Now the formulas for the Green's functions and amplitudes are exactly the same. Yes?
Sorry, to be clear, an arrow moving from x to y would correspond to an electron moving from x to y? So it's the arrows in the direction of negative current?
Right, but it also turns out that positron moving from y to x corresponds to, I mean, it describes either electron moving from here to here or positron moving from there to here. So, yes, we also need to understand how to, in the amplitude calculations, we need to understand how to, what to associate it with external states. And before going to, before describing the external states, let me just show simple examples how to work with propagators and what is the vertex. So the vertex just follows from the fact that the interaction Lagrangian in QED is minus I E A mu psi bar gamma psi. So so what corresponds to this vertex? So we need to, it will appear in the exponent in the master formula. There will be 3 lines ending on this vertex, right? So there will be an electron line that comes in because there is a psi bar. Then there will be another electron line moving out of it because there is a psi. And then there will be a photon line that is emitted from this vertex. And the vertex itself will contain two elements. So let's see. So there is no I here. But there is an I that appears in the formula. So there will be an overall factor of minus I times E. And then there will be a gamma matrix that connects with the indices on psi bar and psi. Yes?
Sorry, I hate to be that person, but are we still using the convention E is negative?
Yes.
All right.
E is negative. That's a weird convention. But what helps is that in whatever expression you get, E always appears as in a square. Yes?
The diagram associated with the vertex contains 3 lines because the interaction term contains 3 fields.
Exactly.
Is one of the lines associated with psi bar and the other associated with psi, or are 2 of the lines associated with psi bar, gamma, mu, psi?
So the vertex itself contains. So in the Feynman rules, the vertex. So that there are, first of all, there are 3 indices in the diagram. Because we need to associate, so the endpoints of propagators now are associated with indices. And so the analytic expression that we should associate with this diagram is equal to minus I gamma mu beta alpha. Times E. Because psi bar was contracted with the gamma, psi bar and psi were contracted with the gamma. So then these indices remain on the propagators. And so this is the vertex that we'll get from the Lagrangian. So let's see how it all works. Yes.
Here you try to expand the action region in terms of E.
In terms of E, yes. So we are expanding
E
it.
So when you are doing the correction in the QED, you always take the ES. So you do the correction in terms of DE.
Yes. We are expanding in E. Actually, in the squared. So
How do we sort of square one reasoning with the other? I thought we did say that what's important in the Heffron constant is the E squared, but here we're using just E. How do we?
That's right. So from Feynman rules, it will. Inspecting the Feynman rules, one can see that only E squared appears. There is a theorem called Farey theorem that proves that no even powers of E can appear. No odd powers. And it can be given a proof, just diagrammatic proof. So let's see. First of all, conventionally, no one writes the Dirac indices. Usually they're suppressed because, as we will see, it's easy to see how they're contracted. But the Lorentz indices are often one writes them explicitly. So, for instance, let's compute correction to the propagator, and we'll only contract the Dirac fields and not worry much about the electromagnetic field. So let's compute corrections to Fermat propagator. So this means that we have we have psi of x Then we have sidebar y. And then we insert interaction vertices. So let's consider correction of second order. So we insert two vertices here. So then we need to do three contractions. So one contraction would look like that. So what we will get in the diagram language, so suppose that this is, okay, so the diagram that we will get will contain one long fermion line with photon lines emanating from it at some points. So the fact that the fermion line cannot get broken is just a charge conservation. So charge cannot disappear. So this electron line, it will continue through the whole diagram. Or the other possibility is that it makes a closed loop. And so when it makes a closed loop, well, let's see. Yeah, what is the analytic expression of this diagram? So if these indices are mu and nu, this will be equal to, and so this is point x, y, z, and w. So the analytic expression is, well, we can just read the diagram from right to left along the electron line. So the first element will be the propagator Sx minus y. Then we have an interaction vertex, so we have a gamma there. So then we have another propagator this is x minus z, z minus w, gamma nu, s w minus y. Then a nu of z contracted with the mu, a nu of w contracted with the nu. And there will be a factor of minus, let's see, minus I e squared. So another possibility is that fermions make a closed loop, and that one should be really accurate because in dealing with fermions, when we rearrange their order, we can pick up a minus sign. So, for instance, let us consider corrections to the photon propagator. So that comes from two vertices of this type. And so let's contract the fermion fields again. So suppose well, let's see. There's just one way to do it, such that the psi's are contracted between the two vertices. So the claim is that this is equal to minus so let's call it So this is psi of x, psi of x. This is psi of y, psi of y. So this will be minus psi of y, psi of x, psi of x, psi of y, and then 2a's. So why so? So to write it this way, we need to pull this field, we need to anti-commute it 3 times. And so each time we anti-commute 2 psi's, we get a minus sign. So there will be an overall minus here. Yes?
Out of curiosity, why is the other pairing like x to x and y to y? Why is that one invalid?
Sorry?
Why is the pairing x to x and y to y invalid?
It will be valid, but well, if you look more carefully, you'll see that it's 0. But in principle, there is such pairing. We just want to study this one. I wanted to give an example where we get a minus sign from anti-commuting fermions. So as a diagram, this looks like that. So we have a photon line, then we have a propagator from x to y, and from y to x. And so here we have contraction of all fermion indices. So the index goes through and is contracted according to matrix multiplication. So the closed loop just means that we take the trace. So what we will get here is minus trace s of x minus y gamma mu s of y minus x gamma nu a mu of x a nu of y, and we should also multiply by minus I e squared.
Why is that a loop corresponds to a trace?
You can write it, if you don't say it immediately, I suggest you to write it with indices just after the lecture. Look how it looks with indices, and then you will see that it's a trace. But, so now, external legs. So if you study scattering of photons and electrons, well, we need to know what to associate it with external factors. So before, in the scalar theory, the factor was just 1. Now, in electrodynamics, it's a little bit more complicated. And this is because particles can appear in different spin states, right? So the scalar particle describes just one particular state. So it has no internal quantum numbers. Photons and electrons do have internal quantum numbers. They have spin. And so we need to specify the polarization of external state. So we can, for instance, study scattering of, I don't know, 2 linearly polarized waves in certain directions. And that we need to specify. And so, well, there is a long list of external factors that one can associate with with various internal and external states. So for photons, it's more or less clear. So if we have a photon with polarization R, then its contraction with the field will leave the polarization vector. Remember that in the expansion of the field in oscillators, the oscillators multiply polarization vector. So when we take the contraction, this polarization vector will remain. So in momentum space, Finnon rules, the incoming photons will carry so we should multiply it by polarization vector. That depends on the momentum k. So for the scalar, we would have had a factor of 1. Here we have a factor of this polarization vector. Yes.
I thought that earlier we said that we could treat A mu as 4 independent scalar fields. So that analogy of A mu to scalar fields does not hold here.
Yeah, it doesn't carry over to external states because external states should satisfy the extra condition that they should be transverse polarized. So the expansion of the field in oscillators contains 4 type of oscillators. 2 of them are unphysical. So they never appear in external states. And therefore, in the external state, we better have, it is characterized, so the external state is characterized not by 4 numbers, but by 2 numbers. I mean, there are 2 degrees of freedom. The photon can have either positive or negative helicity, and that completely characterizes its state. So for okay, so if we have a final state photon, then the contraction gives epsilon r mu complex conjugate e to the ikx. So the outgoing photon will be characterized by momentum and polarization. And the factor that we should write here is epsilon mu r complex conjugate of k. Okay, so we have electrons. So so electrons. Okay, so the Dirac field describes electrons and positrons. So when we have an external particle, then we should assign to it charge and polarization. So we have spin up, spin down, and then we should tell whether it's electron or a positron. You had a question?
Yeah, so I was going to ask what exactly the star of a polarization vector was. Is it just complex?
Just complex conjugation. So if we study circularly polarized waves with with fixed helicity, then it's described by a complex vector.
Oh, right.
So, okay. Now, the field operator contains annihilation operators for electrons and creation operators for positrons. So so when acting on the int state, psi can annihilate only electrons. So it describes an incoming electron and associates to it the wave function u s of p alpha e to the ipx and so a factor associated to the external line will be u alpha s of p. Now, or, so the same field operator can create create a positron. So meaning that it can contract with a positron in the final state. So that would give Vs alpha of p times e to the minus, so that should be minus here, and plus here. So this would correspond to outgoing positron wait a minute. But now you see that outgoing positron is described by the line going inside the diagram. This is because our lines go from so they are this line describes the flow of charge in the diagram, and so in some sense the same line describes positron going back in time, but that's yes.
So for the charge label, positive represents an electron?
Yes, plus corresponds to an electron. So that what corresponds to V S alpha of P. And then psi bar beta of X can contract with the positron in the initial state. That would be given by V bar theta S beta of P, and that would be represented by a line going out of the diagram. So the momentum here, I guess, goes in the opposite direction. So this will be momentum P, and this will be, we'll have index beta here. So finally we have sidebar beta of x. Okay, so this represents the Feynman rules of QED. Now, having these rules, we can compute, in principle, everything. So we can compute probability of any process. And, tomorrow we will do some simplest computations in QED using these Feynman rules. Yes?
So, could you label that exponential term? Is it, the first one is e to the minus IPS, and the next one is to the plus IPS. Is that right?
Yes, so there should be some factors here. There should be this should be with the minus. There should be e to the. So this is just the wave function of. This is the wave function of a positron, and this is the conjugate of the wave function of electron. So the rule of the thumb is the following. So in the incoming lines, we should associate the wave function to each external line with given momentum. And for the outgoing, we should each outgoing line is associated with the conjugate of the wave function. Yes.
Is the momentum there backwards, like it's pointing to it, or should be pointing to the backwards?
Here or
The bottom.
I think it points out of the. Yeah, so the momenta here, they all point out. So the incoming momenta point inside the diagram, for the outgoing particles, they point outside. Okay, let's finish here. Thank you.